December 19th came and went. The world exhaled. 3i Atlas passed at a safe 270 million kilometres, invisible to the naked eye, silent on our instruments, apparently doing nothing more dramatic than following the gravitational laws that govern all objects in space. The media declared victory for normalcy. Just a rock, they said. An unusual visitor, certainly, but ultimately harmless. A curiosity that astronomers would study for years, but that posed no threat to Earth or humanity. The story, as far as the headlines were concerned, was over. Except it's not over. Not even close. Because while the cameras were being packed away and the public's attention moved on to other concerns, a small group of scientists were having a very different conversation. Not about what 3i Atlas is, but about what we can do with it. About whether this object, this interstellar visitor, racing away from us at 60 kilometers per second, might represent something far more valuable than a scientific curiosity. About whether it might be our ticket out of the solar system. The proposal came from Harvard astrophysicist Avi Loeb, the same researcher who's been arguing for years that we should take seriously the possibility that some interstellar visitors might be artificial. But this time, he's not asking whether 3i Atlas is a probe, he's asking whether we can use it as one, whether we can turn this passing object into humanity's fastest spacecraft, whether we can, in his words, hitchhike our way to the stars on the back of something that's already moving faster than anything we've ever built. If you want to follow this investigation through the Jupiter encounter, if you want to understand what happens when this object enters the most powerful magnetic field environment in the solar system and possibly transmits data we're not equipped to intercept, subscribe now and turn on notifications. Because the window for answers is closing fast. The object is fading. The opportunity to act is measured in weeks, not years. And what we decide to do about 3i Atlas might determine whether humanity remains trapped in this solar system or takes its first real step toward becoming an interstellar civilization. It's a radical idea, the kind that sounds like science fiction until you examine the physics and realize it's actually the most practical interstellar transportation proposal anyone's put forward. Because the fundamental problem with space travel isn't technology. It's energy. It's the tyranny of the rocket equation that says you need exponentially more fuel for every increment of speed. It's the fact that our fastest probes, Voyager 1 and Voyager 2, launched nearly 50 years ago and travelling at record-breaking velocities for human-made objects, will take 30,000 years to reach the distance of the nearest stars. 30,000 years! Civilization might not exist that long. The entire span of recorded human history is only about 5,000 years. We're talking about timescales that exceed the lifespan of cultures, of languages, possibly of our species as we currently exist. And that's assuming the Voyager probes survive that long, which they won't because their power systems will fail within the next decade or two and they'll become silent derelicts drifting through the void. But 3i Atlas is moving at 60 kilometers per second, and it's not slowing down. It's on a hyperbolic trajectory that will take it completely out of the solar system and back into interstellar space. If we could attach a payload to that object, if we could use it as a carrier, we could reach the depths of space by the year 10,000 AD. That's still a long time by human standards, still thousands of years, but it's 3 times faster than Voyager. It cuts the travel time by 20,000 years, and it doesn't require us to solve the energy problem, because the energy is already there, stored in the object's tremendous velocity. Before we go deeper into how this might actually work, before we examine the technical challenges and the profound implications of treating interstellar visitors as infrastructure rather than just scientific targets, you need to understand where this story is heading. Because the Jupiter encounter is coming, March 16th, 2026. That's when 3i Atlas will pass within 53 million kilometers of the gas giant. And some researchers believe that's not just a gravitational slingshot, that's a rendezvous. A scheduled stop on a journey that might be far more deliberate than we've been willing to admit. The transport hypothesis changes everything about how we think about these objects. Until now, the conversation has been binary. Either 3i Atlas is a natural comet, a chunk of ice and rock ejected from another planetary system and now passing through ours by chance. Or it's artificial, a probe sent by an extraterrestrial civilization to study our solar system and gather data about Earth. Natural or designed. Rock or technology. Those were the only options on the table. But Loeb's proposal introduces a third possibility. What if objects like 3I Atlas are neither entirely natural nor actively designed for exploration? What if their infrastructure? What if the galaxy is crisscrossed by a network of these fast-moving carriers, objects that travel between stellar systems on predictable routes? And what if civilizations that understand the network can use them for transportation and communication? Think of them as cosmic freight trains. They run on fixed schedules determined by orbital mechanics and gravitational interactions. They don't stop. They don't deviate from their routes. They just pass through. And if you're smart enough and fast enough, you can catch one. You can attach your cargo. You can send your message or your probe or even your biological samples riding on an object that's already moving at speeds you could never achieve on your own. It's an elegant solution to the interstellar travel problem. Instead of building ships that need enormous amounts of energy to accelerate to high velocities, you wait for ships that are already moving to pass by. Instead of fighting the tyranny of the rocket equation, you exploit the kinetic energy that's already present in the galaxy. Objects are being ejected from planetary systems constantly. Gravitational interactions during planet formation scatter material. Some of it falls into the parent star, some of it settles into stable orbits, and some of it gets flung outward at high velocity, becoming interstellar travelers. Those ejected objects are waste from the perspective of natural processes. Debris. Material that didn't make it into planets, and that's now wandering the void with no purpose. But from an engineering perspective, they're resources. They're pre-accelerated spacecraft. They're vehicles that nature has already built and launched, and all you need to do is catch them and use them. The numbers support this. We now know that interstellar objects pass through the inner solar system regularly. We've detected 3 in 8 years, and that's with detection systems that are barely adequate for the task. As our survey capabilities improve, as telescopes like the Vera Rubin Observatory come online and can detect fainter and faster moving objects, the detection rate will increase dramatically. We might find that dozens or hundreds of these objects pass within the inner solar system every year, that they're not rare anomalies but common traffic. If that's true, if the galaxy is full of these travelers, then any civilization that develops spacefaring technology will eventually realize they can use them. We'll eventually figure out that building slow ships is inefficient when fast ships are already passing by. We'll eventually transition from trying to explore the galaxy with their own propulsion to hitching rides on natural infrastructure. And if multiple civilizations make that same realization, if they all start using the same objects for transportation, then the network becomes real, becomes a shared resource. The objects aren't controlled by anyone, they're natural phenomena. But they're being used by everyone who's smart enough to exploit them. This is the paradigm shift Loeb is proposing. We're not just looking at 3I Atlas as a potential alien probe anymore, we're looking at it as potential alien infrastructure, as something that might be carrying cargo from other civilizations, as something we could add our own cargo to, as our entry point into a galactic transportation network that's been operating for millions of years. It sounds fantastic, almost too convenient. But the physics checks out. The economics make sense, and the more you think about the logistics of interstellar travel, the more inevitable the conclusion becomes. If you want to move things between stars, you use what's already moving. You don't waste energy building new ships when the universe is providing them for free. The question is, how do you actually catch one? How do you intercept an object moving at 60 kilometers per second and attach your payload without destroying it or without requiring so much energy that you might as well have built your own ship? Loeb has thought about this. He's proposed several approaches, each with different technical requirements and different levels of ambition. The simplest is non-contact. Use a high-powered laser to engrave a message onto the object's surface as it passes. You're not physically attaching anything, you're just modifying the surface, creating patterns that intelligent observers might recognize as artificial. Writing humanity's name on the side of the cosmic freight train. The laser would need to be powerful, enormously powerful. We're talking about megawatt-class systems, probably arrays of lasers working in coordination to deliver enough energy at interstellar distances to ablate material and create visible marks. But this is technology we're developing anyway for other purposes. The Breakthrough Starshot project, designed to send tiny probes to Alpha Centauri using laser propulsion, requires similar laser arrays. If we can build the infrastructure for Starshot, we can repurpose it for engraving. The advantage of this approach is that it doesn't require matching the object's velocity. You're hitting it with light, and light travels at light speed regardless of the target's motion. The disadvantage is that you're not actually sending anything physical. You're just creating a signal, a sign that intelligence exists here, that we noticed the object, that we're capable of reaching out across millions of kilometers with coherent energy. Is that enough? Does it accomplish anything meaningful? Maybe. If the object is being monitored, if there are civilizations checking these carriers for modifications, then an engraved message might trigger a response, might result in a reply being engraved onto another object that passes through our system decades or centuries later. It's slow communication. Generational timescales. But it's communication nonetheless. The more ambitious approach is physical attachment. Design a small probe, something lightweight and robust, and accelerate it to match the object's velocity. Or get close enough that you can use harpoons or adhesives or magnetic clamps to attach despite a velocity mismatch. This is harder, much harder. The energy requirements to accelerate even a small payload to 60 kilometers per second are substantial. You'd need either nuclear propulsion, or advanced ion drives, or maybe even laser-pushed light sails. But it's not impossible, it's engineering rather than physics. If you could attach a probe, you could send actual data. Not just a message, but a library, a comprehensive record of human civilization. Everything we know about ourselves and our world, encoded in a format that might be decipherable by other intelligences, DNA sequences, cultural artifacts, scientific knowledge, the entire accumulated wisdom of the species, riding into the galaxy on the back of an interstellar visitor. Loeb has said publicly that he would be willing to donate his own biological remains to such a mission. To have his DNA carried out into the galaxy is poetic. The idea of becoming an interstellar traveller after death, of having your genetic code persist long after the civilization that produced you has risen and fallen, of potentially being reconstructed by future intelligences who might study the samples and wonder about the beings who sent them. But it also raises profound questions. If we're sending biological samples, are we seeding the galaxy? Are we engaging in panspermia, the distribution of life across stellar systems? And if we're willing to send our biology outward, should we be concerned that other civilizations might have done the same? That 3i Atlas itself might be carrying samples? That it might have deposited material in our solar system? This is where the transport hypothesis gets darker, because a transport system works both ways. You can send cargo out, but you can also receive cargo in. And if 3i Atlas approached Earth, if it came within 270 million kilometers at closest approach, if it was shedding material during that encounter, then maybe it wasn't just passing through. Maybe it was making a delivery. The spectroscopic data shows that the object's coma contains organic molecules, hydrogen cyanide, cyanogen, complex carbon compounds. The standard explanation is that these are natural components of cometary ice, formed in molecular clouds and preserved since the object's creation billions of years ago. But if you're thinking about transport systems, if you're considering that the object might be deliberately carrying cargo, then those organic molecules start to look less like contaminants and more like payload. What if the cyanide isn't random? What if it's packaged? What if the molecules we're detecting are inside protective capsules designed to survive the harsh environment of space and deliver their contents to target worlds? What if 3i Atlas has been seeding every planetary system it passes through with the chemical building blocks of life? It's speculative, wildly so. But it fits the pattern. If you're a civilization that's discovered how to use interstellar objects for transportation, you might also discover how to use them for terraforming, for distributing life across the galaxy. You load up the carriers with biological precursors, you send them on trajectories that pass through promising stellar systems, and you let natural processes do the rest. The molecules land on planets, they enter atmospheres and oceans, and over billions of years they contribute to the development of life. This is directed panspermia, the idea that life didn't arise independently on every world, but was seeded deliberately by advanced civilizations trying to make the galaxy more biologically diverse. It's been proposed before, usually dismissed as untestable speculation. But if 3i Atlas is a transport, if it's carrying organic cargo, then we might be witnessing directed panspermia in action. We might be on the receiving end of a process that's been shaping biology across the galaxy for eons. And if that's true, then maybe life on Earth didn't arise purely from local chemistry. Maybe we're the descendants of molecules delivered by ancient visitors. Maybe our DNA contains sequences that originated in other stellar systems. Maybe humanity itself is part of the network, connected to civilizations we've never met through shared biological heritage. It's a staggering thought, and it's probably wrong. The evidence doesn't support it. The organic molecules in 3I Atlas's coma are too simple, too common, to represent engineered cargo. They're exactly what you'd expect from natural cometary outgassing. Reading more into them requires assumptions that aren't justified by the data, but the fact that we're even having this conversation, the fact that researchers are seriously considering whether interstellar objects might be transport systems carrying biological cargo, shows how much the paradigm has shifted. We're not just asking what these objects are anymore, we're asking what they might be used for, what role they might play in galactic ecology and civilization, what opportunities they might offer humanity if we're brave enough to exploit them. The technical challenges remain enormous. Catching a freight train moving at 60 kilometers per second is not a trivial engineering problem, but Loeb argues that it's more achievable than building our own interstellar ship. That using existing infrastructure is always more efficient than creating new infrastructure from scratch. That if we're serious about becoming an interstellar civilization, we need to stop thinking about building ships and start thinking about catching rides. And the window is closing. 3I Atlas is moving away. Every day it gets farther from Earth and harder to intercept. If we're going to act, if we're going to attempt to attach a payload or engrave a message, or even just closely study the object before it fades from view, we need to do it soon. Within months, not years. The object won't wait for us to make up our minds. But before we can decide what to do about 3I Atlas, we need to understand what it actually is. And this is where the latest data becomes deeply confusing. Because the new size estimate doesn't make sense. The new analysis suggests the nucleus is approximately 1 kilometer in diameter. 1 kilometer, that's small. Significantly smaller than many long-period comets. Smaller than the city-killer asteroids we track for planetary defense. It's a modest chunk of ice and rock by astronomical standards. But here's the problem. A 1 kilometer object shouldn't be behaving the way 3I Atlas is behaving. The observations show massive outgassing. A bright coma extending hundreds of thousands of kilometers, a prominent tail, all of which require shedding substantial amounts of material, and the mass loss rate calculated from the brightness and spectral data is high, consistent with vigorous sublimation driven by solar heating. If you're a 1 kilometer chunk of ice and you're venting gas at these rates, you should be falling apart. The structural stress should exceed the object's tensile strength. The thermal gradient should create cracks. The internal pressure from sublimating ice should fracture the nucleus. We've seen this happen with other comets, objects that look solid at first, but that disintegrate under the stress of close solar passage. 3I Atlas hasn't disintegrated, it's held together. Remained intact despite months of exposure to solar heating and despite mass loss that should have weakened its structure. The nucleus appears stable in all the high-resolution images we've captured. No fragmentation events, no major structural changes, just steady, sustained activity. This creates a paradox. Either the object is made of something incredibly strong, something that can withstand stresses that would destroy normal cometary ice, or the outgassing isn't what it appears to be. Either the material has properties we don't see in solar system comets, which is possible for an object formed in a different stellar environment, or the gas we're observing isn't coming from thermal sublimation but from some other process. And this is where speculation about artificial origin creeps back in. Because if 3I Atlas is a machine, if it's a 1 kilometer hull rather than a 1 kilometer rock, then the structural integrity makes sense. Engineered materials can be strong, can be designed to handle thermal stress and internal pressure without failure. And the gas we're seeing in this scenario isn't sublimation, it's exhaust. Propellant being vented deliberately to create thrust. The non-gravitational acceleration supports this. The object is moving faster than gravity alone can explain. It's experiencing a push. The mainstream explanation is that this push comes from outgassing, from the rocket effect created when gas escapes asymmetrically from the nucleus. But if the nucleus is 1 kilometer across and made of ice, the amount of gas required to create the observed acceleration should have destabilized the structure, unless the push isn't random, unless it's controlled, unless 3I Atlas is executing course corrections, firing thrusters to maintain a specific trajectory and ensure it hits the Jupiter encounter window with precision. This is the darker interpretation of the transport hypothesis, Not that we can use these objects, but that someone else is using them. That 3i Atlas isn't just infrastructure available for anyone to exploit, that it's an active vehicle under control, that it has a mission and a destination, and that its passage through a solar system was planned rather than coincidental. The trajectory supports this interpretation uncomfortably well. The object entered the solar system from above the ecliptic plane, the disk where most planets orbit. It dove down toward the Sun, passed through the inner system, approached Earth at a safe but measurable distance, and is now heading toward Jupiter at an angle and velocity that will result in a close encounter on March 16, 2026. If this were a random object, if it were just falling through the solar system under gravity, you'd expect a simpler path, a hyperbolic arc determined by entry velocity and solar gravity. But the actual trajectory is more complex. The non-gravitational acceleration creates deviations. The path bends in ways that pure gravity doesn't predict, and the deviations, when you analyze them carefully, look less like random outgassing and more like deliberate navigation. Threading past Earth and then threading past Jupiter requires precision. The margins are tight. If the velocity was slightly different, if the entry angle were off by even a fraction of a degree, the object would miss one or both encounters. But it's not missing, it's hitting the windows perfectly. And that precision, combined with the structural anomalies and the size paradox, creates a pattern that's increasingly difficult to explain through natural processes alone. This is why some researchers are starting to talk about interception not as a scientific opportunity, but as a strategic necessity. Because if 3i Atlas is under control, if it's gathering data about our solar system and preparing to transmit that data when it reaches Jupiter, then letting it complete its mission might not be in humanity's best interest, especially if the data it's carrying includes information about Earth's defenses, about our technological level, about our biological vulnerabilities. The Jupiter encounter becomes critical in this scenario, because Jupiter's magnetic field is the most powerful in the solar system. It extends millions of kilometers into space, it creates intense radiation belts, and it acts as a natural amplifier for electromagnetic signals. If you wanted to transmit data across interstellar distances, if you needed to boost your signal to reach receivers light years away, Jupiter would be the perfect relay station. Position yourself near the planet, use its magnetic field as an antenna, and broadcast at frequencies and power levels that wouldn't be achievable from your onboard systems alone. The planet becomes your transmitter, and anything you've recorded during your passage through the inner solar system gets sent outward into the galaxy at signal strengths that could reach other stellar systems within decades or centuries. This is speculation built on speculation. There's no evidence that 3i Atlas is planning to transmit from Jupiter. No detected signals that would indicate communication capability, no reason beyond geometric coincidence to think the Jupiter encounter is anything more than a gravity assist. But the possibility exists, and if the object is artificial, if it's operating under control, then the possibility becomes a probability. Because Jupiter is the obvious choice for a relay. Any intelligent mission planner would use it, and if transmission happens, if 3i Atlas uploads its data when it reaches Jupiter, then there's nothing we can do to prevent the information from reaching its destination. We can't intercept electromagnetic signals travelling at light speed, can't block them or redirect them. Once the transmission starts, it's out of our hands. The data goes into the galaxy, and we have no control over who receives it or what they do with it. This is the nightmare scenario that's driving discussions about kinetic interception. The idea that maybe we shouldn't let the object reach Jupiter, that maybe we should destroy it while we still can, use missiles or lasers or some other weapon system to fragment the nucleus and prevent transmission. It sounds aggressive, paranoid even. But if you take seriously the possibility that 3i Atlas might be reporting back to its creators, if you consider what information it might have gathered during its approach to Earth and what that information could be used for, then preemptive action starts to look less like aggression and more like prudence. But there's a problem with this approach. Actually, multiple problems. First, we don't have weapon systems capable of reaching the object. It's too far away and moving too fast. Our missiles can't catch it. Our directed energy weapons might be able to hit it if we had weeks to prepare and coordinate between multiple ground stations. But we don't have that kind of infrastructure ready. The breakthrough Starshot laser array, designed for pushing light sails toward Alpha Centauri, could theoretically be repurposed for this, but it's not fully built yet, and using it as a weapon would require political decisions that haven't been made. Second, even if we could hit the object, we don't know what would happen. Fragmenting a 1-kilometer nucleus doesn't make it disappear. It creates debris, lots of debris, thousands of smaller pieces all travelling on similar trajectories. Some of them might be deflected by the explosion, but many would continue toward Jupiter, and if the object has redundant systems, if the mission can survive fragmentation, then we've accomplished nothing except spreading the problem across a wider area. Third, and most troubling, we don't know if the object is alone. The new data mentions fragment ejection. The paper analysing the non-gravitational acceleration notes that the momentum changes could be caused by the object shedding pieces of itself, not just gas, solid fragments. The mainstream interpretation is that these are ice chunks breaking off as the nucleus heats and cracks. But if you're thinking about transport systems, if you're considering deliberate deployment, then fragment ejection starts to look like something else. It starts to look like the object dropping off cargo, releasing smaller probes or sensors or seeds, scattering payload across the inner solar system while the main carrier continues outward. And if that's happening, if 3i Atlas isn't just passing through, but is actively deploying assets in our solar system, then attacking the main object accomplishes nothing. The fragments are already here, already in orbit, already doing whatever they were designed to do. This is where the conversation shifts from astronomy to something that feels more like military intelligence. Because if there are fragments, if small objects were ejected from 3i Atlas during its passage near Earth, then we need to find them, need to track them, need to understand what they are and what they're doing before we can assess whether they represent a threat or an opportunity. And there are hints, circumstantial and ambiguous but present in the data, that something unusual is happening in Earth's orbital neighbourhood. Reports of meteor activity that doesn't match known streams, sightings of slow-moving fireballs entering the atmosphere at unusual angles, anomalies in satellite operations that might indicate drag from unexpected sources, GPS glitches, communication disruptions, small things individually, possibly unrelated, but clustering in time around the December 19th closest approach, in ways that make pattern-seeking minds suspicious. Are these signs of fragment activity? Are we seeing debris from 3i Atlas interacting with Earth's atmosphere and orbital infrastructure? Or are we seeing random noise being retroactively connected to the comet? Because humans are good at finding patterns even where none exist. The data isn't clear enough to decide, but the possibility is there. The concern is real, and it's driving a level of attention to Earth's near-space environment that hasn't been seen since the early days of satellite tracking during the Cold War. We're watching for things that shouldn't be there, tracking objects that don't match known catalogues, trying to distinguish between the thousands of pieces of human-made debris already in orbit and anything new that might have been added by an interstellar visitor. It's difficult work. Orbital space is crowded. The number of tracked objects exceeds tens of thousands, and that's just the larger pieces. Smaller fragments number in the millions. Finding something new, something that wasn't there before December 19th, requires careful analysis of observation records and the ability to distinguish between objects that have always been there but weren't being tracked and objects that genuinely appeared recently. But the effort is underway. Multiple agencies, government and private, are now focusing resources on comprehensive sky surveys and orbital monitoring, looking for anomalies, searching for the fragments that might have been deployed, trying to answer the question of whether 3i Atlas came alone or whether it left pieces of itself behind. And while that search continues, while we try to understand what's already here, the main object keeps moving, keeps accelerating away from the Sun, keeps heading toward its March 16th appointment with Jupiter. The distance from Earth is now over 270 million kilometers and growing. The brightness is fading. The window for detailed observation is closing. Soon, within weeks, the object will drop below the detection threshold for all but the largest telescopes. Will become a faint point of light barely distinguishable from background stars. Will fade from our instruments the same way it faded from public consciousness, and then it will be gone, out of reach, beyond our ability to intercept or study or engage with in any meaningful way, unless we act, unless we make decisions now about what humanity's response should be. Do we try to send a message using lasers? Do we attempt a physical intercept despite the enormous technical challenges? Do we prepare weapon systems for a strike against the object before it reaches Jupiter? Do we simply watch and gather data and hope that our passive observation yields answers without requiring us to commit to action? These are not just technical questions, they're philosophical ones, about what kind of civilization we want to be, about whether we approach the unknown with curiosity or fear, about whether we're willing to take risks to reach out to potential neighbours, or whether we choose the safety of silence and isolation. The decisions being made now, in classified meetings and academic conferences, and informal discussions among researchers who understand what's at stake, will shape humanity's relationship with the cosmos for generations. Will determine whether we become participants in whatever network exists among the stars, or whether we remain spectators, watching from the sidelines as other civilizations exploit infrastructure we're too afraid or too slow to use. 3i Atlas is still here, still visible, still within reach if we move quickly, but the window is measured in weeks, and every day of debate, every hour of hesitation makes action harder and reduces our options. The freight train is leaving the station. The question is whether humanity will try to catch it, or just wave goodbye as it disappears into the dark. The radio silence is what haunts the researchers. Not the absolute silence, but the qualified silence, the carefully measured silence that comes with numbers attached. Because when the Allen Telescope Array pointed its dishes at 3i Atlas for over 7 hours on July 2nd, when they listened across multiple frequency bands with sensitivity calibrated to detect the faintest whispers of artificial transmission, they didn't find nothing. They found something, and then they explained it away. 74 million signals. That's how many hits the system recorded during those 7 hours. 74 million potential detections. Before you get excited, before you imagine that we've intercepted a massive data stream from an alien probe, understand that this is normal. The sky is full of noise, satellites broadcasting on hundreds of frequencies, GPS signals bouncing off the ionosphere, ground-based transmitters leaking into space, cosmic background radiation, solar emissions. The electromagnetic spectrum is crowded. Finding signals is easy. Finding meaningful signals is extraordinarily difficult. The researchers know this. They've developed sophisticated filtering algorithms designed to strip away all the known sources of interference. They remove satellite transmissions by comparing signal directions with known orbital positions. They eliminate GPS and communication bands because we know what those look like. They filter out solar noise and cosmic background based on spectral characteristics. It's a process of elimination. You start with millions of signals and you remove everything you can explain until you're left with the residue, the anomalies, the hits that don't match any known source. After filtering, they were left with 211 signals, 211 transmissions that came from the direction of 3i Atlas, and that didn't match the signature of any known interference source. That should have been the headline, should have been the discovery. 200 detections from an interstellar object that some researchers believe might be artificial, except they dismissed them. The researchers examined the waveforms visually, looked at the frequency distributions and the temporal patterns, and they concluded that these 201 signals, while unusual, were not worthy of additional follow-up. Just noise, statistical fluctuations, the inevitable false positives that emerge when you're looking at millions of data points and applying imperfect filters. Maybe they're right. Maybe those 211 signals were nothing. Random interference that happened to come from the right direction at the right time. Coincidence. Noise that slipped through the filters because the filters, however sophisticated, can't be perfect. Or maybe they dismissed them too quickly. Maybe the signals were real but subtle, encrypted, compressed, using modulation schemes we don't recognize because they weren't designed for human receivers. Maybe the researchers were looking for obvious patterns, clear beacons, the kind of hello world transmission that would be unmistakable. And maybe what 3i Atlas was actually sending was something far more sophisticated. Data streams that look like noise unless you have the decryption key. But there's another number that came out of that observation campaign, a number that's arguably more interesting than the 211 dismissed signals. The researchers established an upper limit on transmission power. Based on the sensitivity of their instruments and the lack of clear detections, they calculated that if 3i Atlas is transmitting, the power level must be between 10 and 110 watts. Let that sink in. 100 watts. That's a light bulb. That's the power consumption of a laptop computer. If there's a transmitter on this object, if it's broadcasting as it passes through the solar system, it's doing so with less power than your kitchen microwave uses. Why would an interstellar probe use such low power? The conventional explanation is that it's not transmitting at all, that the upper limit simply reflects the fact that there's no artificial signal to detect. But if you're willing to entertain the possibility that the object is artificial, if you accept that it might be transmitting but below our detection threshold for obvious signals, then low power becomes interesting rather than dismissive. Low power transmission makes sense for two reasons: energy conservation and stealth. If you're operating on limited power reserves, if you're millions of years into a mission and your systems are degraded and you need to make your remaining energy last as long as possible, you don't waste watts broadcasting omnidirectional beacons. You use directed beams, narrow transmissions aimed at specific targets, high-gain antennas that focus your power into tight cones rather than spreading it across the entire sky. A 100-watt transmitter with a high-gain antenna can achieve the same effective radiated power as a kilowatt omnidirectional broadcaster, but only in the direction the antenna is pointing. From any other angle, you'd detect nothing or almost nothing. And if the antenna isn't pointed at Earth, if 3i Atlas is transmitting toward Jupiter or toward some distant relay station we don't know about, then the Allen telescope array would have been looking at the side of the beam, would have been outside the main transmission cone, would have detected only the weak side lobe leakage that any antenna produces. That could explain the 211 signals. Not noise, but side lobe spillover. Fragments of a directional transmission that the filters couldn't quite eliminate because they're real signals, just not intended for our receivers. The researchers looked at the waveforms and saw nothing structured enough to convince them it was artificial. But if the transmission was encrypted, if it was compressed data rather than an obvious beacon, the waveform would look random, would look like noise, would be indistinguishable from background static unless you had the algorithm to decode it, and stealth. If you're a surveillance probe, if your mission is to study planetary systems without being detected, you don't broadcast loudly, you don't announce your presence, you operate in whisper mode, low power, directional beams, burst transmissions that last only milliseconds and that send compressed data packets too brief to be easily analysed. You phone home periodically to upload your observations, but you do it in ways that minimise the chance of interception by the civilization. You're studying. This is standard tradecraft for intelligence operations. You don't leave obvious fingerprints. You don't give your targets tools they can use to track you. You stay quiet, stay small, stay below their detection thresholds. And if 3i Atlas is a probe designed to study developing civilizations, if it's been doing this for millions of years across hundreds of stellar systems, then it would have learned long ago that obvious transmissions draw attention. That silence is safer than conversation. The low power limit, therefore, doesn't rule out artificial transmission. It just constrains the type of transmission to something subtle, something we might not recognize even if we're listening directly to it. And that's frustrating because it means we can't definitively answer the question. Can't say with certainty whether the object is transmitting or silent. Can only establish upper bounds and wonder whether the real signal is hiding just below our ability to detect it. But there's another possibility, one that researchers are discussing in private but haven't stated publicly, because it sounds too much like paranoid speculation. What if the low power isn't about conservation or stealth? What if it's about the intended receiver? Earth is not the target, we're not the audience. The transmission isn't meant for us, it's meant for a relay. And the relay is at Jupiter, March 16th, 2026. That's when 3i Atlas reaches its closest approach to the gas giant. 53 million kilometers. In astronomical terms, that's intimate, close enough to be strongly influenced by Jupiter's gravity, close enough to feel the intense magnetic field, close enough to use the planet's magnetosphere as an amplifier. Jupiter's magnetic field is the most powerful in the solar system. It extends millions of kilometers into space, creating a vast bubble of trapped charged particles and electromagnetic activity. That field doesn't just deflect the solar wind and create radiation belts, it also acts as a natural antenna, a massive electromagnetic structure that can receive and transmit signals across enormous distances. If you're designing an interstellar communication network, if you're trying to send data between stellar systems using minimum energy, you don't build your own transmitters at every location. You use what's already there. You use the natural infrastructure. Gas giants with strong magnetic fields become relay stations. You position your probes to pass close to these planets. You upload your data in a short high-power burst when you're near enough to couple to the magnetosphere. and you let the planet boost your signal. From 53 million kilometers, a 100-watt transmitter can couple to Jupiter's magnetic field with far more efficiency than broadcasting across interstellar space on its own. The planet becomes the antenna, the magnetosphere becomes the amplifier, and the transmission, instead of fading to undetectability within a few astronomical units, can reach across light years, can arrive at receiver stations in other stellar systems with signal strength sufficient for decoding. This is why some researchers believe the Jupiter encounter isn't just a gravity assist. It's the whole point of the mission. 3I Atlas spent months in the inner solar system, passed close to Earth, gathered data using whatever sensors it possesses, and now it's carrying that data to the upload point, to Jupiter, where it will transmit everything it's learned in a compressed burst that might last only seconds, but that will contain terabytes of information about our solar system, our planet, our civilization. And we won't be able to stop it. Can't block electromagnetic transmission once it starts. Can't jam signals at that power level across the distances involved. The only way to prevent the upload would be to destroy 3I Atlas before it reaches Jupiter, to fragment it, or disable it while it's still far enough from the planet that the debris can't continue the mission. This is the ticking clock scenario, the deadline that's driving discussions about kinetic interception and weapon deployment. If you believe the object is reporting back, if you think the Jupiter encounter is a scheduled upload to a galactic communication network, then you have until March 16th to act. After that, the data is in the system, the information about Earth is transmitted, and whatever consequences follow from that transmission are beyond our control. But destroying the object requires capabilities we don't currently have deployed, requires making decisions about the use of force against what might be a scientific probe, requires accepting that we might be attacking something harmless out of fear based on incomplete evidence. It's a gamble with enormous stakes and no clear right answer. And there's a complication that makes the decision even harder. The fragments. Because if the object has already deployed payload in Earth orbit, if it's already dropped off the surveillance package or the seed capsules or whatever cargo it was carrying, then destroying the main carrier accomplishes nothing except announcing to whoever sent it that we're hostile, that we respond to visitors with violence rather than curiosity. The fragment hypothesis is where the transport theory gets truly unsettling, because the new analysis of 3I Atlas's trajectory mentions something that most press coverage glossed over. The non-gravitational acceleration, the extra push that the object is experiencing beyond what solar gravity provides, could be explained by fragment ejection, by the object shedding pieces of itself. The mainstream interpretation is thermal, ice chunks breaking off as the nucleus heats, cracking and fragmentation driven by thermal stress. Normal cometary behavior, nothing unusual except the scale, which is high for such a small nucleus, but not impossible if the material has the right properties, but timing matters, and the fragments, according to the analysis, were ejected primarily during the perihelion passage, during the period when 3I Atlas was closest to the Sun and also closest to Earth. If you were deploying sensors or probes or biological samples, that's exactly when you do it. You use the gravitational slingshot to scatter your payload across the inner solar system. You release objects on trajectories calculated to intersect with planetary orbits, or enter stable positions at Lagrange points. The ejection gives them velocity, kicks them away from the main carrier with enough energy to change their orbits independently, and because they're small, because they're released among the dust and gas of the coma, they're nearly invisible, lost in the noise, camouflaged by the natural debris field surrounding the comet. How many fragments? The papers don't specify. The estimates are vague. Could be dozens, could be hundreds, could be thousands of small objects, each one following its own trajectory, each one potentially carrying sensors or samples or instructions. We don't know because we can't track objects that small at those distances unless they're actively emitting or reflecting unusual amounts of light. But some of them might be coming down, might be entering Earth's atmosphere, and this is where the anecdotal reports start to matter. The sightings of unusual meteor activity, fireballs that don't match known meteor streams, objects entering at shallow angles suggesting they're in Earth-like orbits rather than falling in from the outer solar system. The reports cluster around late December, around the time when debris from the December 19th encounter would be reaching Earth if it was ejected on specific trajectories. The meteors are described as slow, orange, entering at angles that suggest they're catching up to Earth rather than hitting head-on. That's the signature of objects in similar orbits, objects that were near Earth, that were released in Earth's vicinity and that are now spiralling in under atmospheric drag. Are these fragments from 3I Atlas? Or are they the tail end of the Geminid meteor stream, which peaked in mid-December but can produce stragglers for weeks afterward? Or are they random space debris, satellites re-entering, natural meteors from unknown parent bodies? The data is ambiguous. Amateur astronomers report the sightings, but amateur observations are notoriously unreliable. Colours can be misperceived, angles can be misjudged, memory is reconstructive and subject to bias. People who've been reading about 3I Atlas and who see a meteor are more likely to remember it as unusual, more likely to connect it to the comet, than people who haven't been following the story. But there are other anomalies, more difficult to dismiss. Reports from commercial pilots of GPS disruptions over the Pacific, satellite operators noting unexpected drag on spacecraft in low Earth orbit, Starlink experiencing anomalous signal degradation. Small things, individually explainable, but clustering in time in ways that make analysts at space agencies pay attention. GPS disruption can come from solar activity, from geomagnetic storms, from intentional jamming by military systems. The Pacific routes are heavily travelled, and interference is not uncommon. But when you cross-reference the timing with the 3I Atlas encounter, when you note that the disruptions began shortly after December 19th and have been intermittent but persistent since then, pattern recognition kicks in. Satellite drag is even more interesting. Objects in low Earth orbit experience atmospheric drag that gradually lowers their altitude and requires periodic reboosting to maintain position. The drag is predictable based on solar activity and atmospheric density. But several satellites have reported higher than expected drag over the past weeks. Not enormously higher, not enough to cause operational problems, just enough to be noticeable, enough that orbital mechanics teams are scratching their heads and trying to figure out why their models aren't matching observations. Could be atmospheric changes, could be solar wind variations we didn't predict, could be measurement errors or modelling assumptions that need refinement, or could be objects in orbit that we're not tracking. Small dense fragments that are creating drag on satellites when they pass through the same orbital shells. Debris that's adding to the particle density in near-Earth space. SpaceX has been quiet about Starlink issues. They don't publicly discuss operational anomalies unless they're severe enough to impact service. But insiders speaking anonymously on forums and in private communications mention that certain satellites in the constellation have been experiencing signal problems, unexpected fading, brief dropouts, interference that doesn't match any known source. Is this related to 3I Atlas? Impossible to say. The evidence is circumstantial at best, correlation without proven causation, but the timing is suspicious, and the pattern, if there is a pattern, suggests that something changed in Earth's orbital environment around December 19th. Something small enough to evade detection, something distributed enough that individual incidents seem random, but something real. If the fragments exist, if 3I Atlas deployed objects during its passage, then we need to find them, need to catalogue them, need to understand what they are before we can assess risk or opportunity. And finding them requires comprehensive sky surveys and enhanced space tracking. Requires treating Earth's orbital neighbourhood as potentially contaminated and sweeping it for objects that shouldn't be there. The effort is underway, not publicly, not with press releases and official statements, but behind closed doors, space agencies are dedicating resources to the problem, are tasking radar systems to look for small objects in unusual orbits, are analysing orbital debris, catalogues for entries that appeared recently, are sharing data between agencies that normally keep their information classified. It's difficult work. The number of objects already in Earth orbit is staggering. Tens of thousands of tracked pieces of debris, millions of smaller fragments. Finding a few dozen or a few hundred new objects among that population is like finding needles in a haystack made of needles. You need to know what you're looking for, need to have signatures or characteristics that distinguish the targets from background noise. And we don't know what we're looking for. If the fragments are technological, if they're designed to avoid detection, they might be optimized to be dark and non-reflective and thermally cold. Might be using stealth characteristics that make them invisible to radar and optical tracking. Might be sitting in orbits we don't normally survey because we assume those regions are empty. The Lagrange points are of particular concern. These are positions in space where the gravitational forces of Earth and Sun balance in ways that create stable parking spots. Objects placed at Lagrange points don't need propulsion to maintain position. They just sit there, permanently. observing, recording, waiting. L4 and L5, the points 60 degrees ahead and behind Earth in its orbit, are particularly stable. Objects there can remain for millions of years without drifting. We've detected some natural asteroids at the Earth-Sun Lagrange points, small rocky bodies that got captured gravitationally and that now share Earth's orbit. But we haven't surveyed those regions comprehensively, haven't catalogued everything that's there, and if 3i Atlas deployed objects to L4 or L5, if it placed observers at the points with the best long-term stability, we might not find them unless we specifically look. And even if we find them, what then? If we detect objects at the Lagrange points that we can't explain, that don't match any known spacecraft or natural bodies, what's the response? Do we send missions to retrieve them? To study them up close? Do we attempt communication? Try to trigger responses that might reveal whether the objects are active or dormant? Or do we destroy them? Use the same kinetic interceptors and laser systems being discussed for attacking the main body of 3i Atlas? Eliminate the fragments before they can complete whatever mission they're on? The ethical implications are staggering. Because if these objects are probes, if they're scientific instruments sent by another civilization to study our solar system, then destroying them is not self-defense. It's vandalism. It's the destruction of property that doesn't belong to us. It's an act of aggression against beings we've never met based on fear rather than evidence of hostile intent. But if the objects are weapons, if they're surveillance platforms gathering intelligence for future invasion, if they're biowarfare vectors designed to seed Earth with pathogens or alter our biosphere in ways that benefit their creators, then failing to destroy them is negligence, is allowing a clear and present danger to operate freely in our orbital space. The problem is we can't tell the difference, can't distinguish between scientific instruments and weapon systems without close examination, can't assess intent without communication, and we don't have frameworks for making these decisions, don't have protocols established for how to respond to potential alien artifacts in Earth orbit. So the debate continues, in classified briefings and academic conferences, in informal discussions between researchers who understand the stakes, and in formal policy meetings where officials try to balance scientific curiosity against security concerns. And while the debate continues, the clock ticks toward March 16th. Because regardless of whether the fragments exist, regardless of what we decide to do about potential objects in Earth orbit, the main body of 3i Atlas is still heading toward Jupiter, is still accelerating outward, is still apparently on track for a close encounter that might be a relay upload or might be just a gravitational slingshot that happens to have convenient timing. The distance from Jupiter is decreasing daily. The approach trajectory is becoming more precise as additional observations refine the orbital calculations. And the uncertainty is narrowing. We know, within tight margins, exactly when and where the encounter will occur. Know that on March 16th, 2026, 3i Atlas will pass within 53 million kilometers of the gas giant. What we don't know is what will happen during that passage, whether the object will simply swing past, stealing momentum from Jupiter's gravity and continuing outward at even higher velocity, or whether it will do something, transmit, maneuver, release additional payload, execute whatever mission protocol is programmed for the Jupiter encounter, and we don't know whether we'll be able to observe it. Because while we have assets at Jupiter, they're not designed for tracking fast-moving interstellar objects. Juno is there, orbiting the planet, studying its atmosphere and magnetic field. But Juno's instruments are pointed at Jupiter, not at passing visitors. The cameras are optimized for imaging clouds and auroras, not for capturing objects moving at tens of kilometers per second. NASA has stated, carefully and with appropriate caveats, that they don't expect Juno to get useful close-up images of 3i Atlas during the encounter. The geometry is wrong. The object will be too far from Juno's orbit. The relative velocities are too high. Juno Cam, the public outreach camera, might catch a glimpse if the timing is perfect, but it won't be the high-resolution imagery that would reveal surface features or structural details. But there are other instruments, radio receivers, magnetometers, particle detectors. If 3i Atlas transmits during the encounter, if it couples to Jupiter's magnetic field and broadcasts using the planet's magnetosphere as an amplifier, Juno should detect the electromagnetic signature, should see variations in the field strength and configuration that don't match natural processes, should record emissions at frequencies and power levels that indicate artificial origin. This is the test. the observation that might finally settle the question of whether 3i Atlas is natural or designed. Because natural comets don't emit structured radio signals, don't create coherent transmissions that modulate Jupiter's magnetic field. If we detect that, if Juno records clear evidence of artificial electromagnetic activity during the flyby, then the debate ends. Then we know with certainty that we're dealing with technology. And if we detect nothing, if the encounter passes without any unusual electromagnetic signatures, then the artifact hypothesis becomes much harder to defend, not impossible. There are scenarios where a silent flyby is consistent with designed origin, but the lack of transmission would suggest that either the object isn't artificial, or that its mission doesn't include uploading data at Jupiter. So everyone is watching, waiting, preparing instruments and analysis pipelines, getting ready for March 16th when either everything changes, or we confirm that our paranoia was unwarranted, and 3i Atlas is just a weird rock following physics and nothing more. But there's a darker possibility, one that keeps security analysts awake at night. What if we're not supposed to detect the transmission? What if the signal is encrypted with quantum algorithms we can't break? What if it's using modulation schemes or frequency bands we don't monitor? What if the upload happens and we completely miss it, because our instruments aren't sophisticated enough to recognize what they're seeing? Then we'd observe the encounter, record data, analyze it thoroughly, and conclude that nothing unusual happened. While in reality, while we're congratulating ourselves on ruling out the artifact hypothesis, the transmission would be complete, the data about Earth would be in the network, and we'd be none the wiser. This is the intelligence analyst's nightmare, the scenario where you're being watched and you don't know it, where your enemy is operating in your space using capabilities you don't understand and countermeasures you can't deploy, where you think you're safe, but you're actually compromised, and by the time you figure it out, it's too late to respond. If 3i Atlas is sophisticated, if it's the product of a civilization thousands or millions of years more advanced than us, then our instruments are stone knives compared to their technology. Our attempts to detect their transmissions are like trying to intercept fiber optic communications using a crystal radio. The signals might be passing right through our detectors without triggering any response because we're not looking at the right parameters, and that possibility, that we might be completely outmatched technologically, is what drives some researchers to advocate for aggressive interception. For destroying the object not because we know it's hostile, but because we can't afford to assume it's benign. Better to err on the side of caution, they argue. Better to eliminate a potential threat even if there's a high probability it's harmless, than to let it operate freely and discover too late that it wasn't harmless at all. The counter-argument is that attacking a potentially artificial object could trigger responses we're not prepared for. If the fragments exist, if they're in Earth orbit, they might have defensive protocols, might be programmed to react if the mothership is threatened, and we don't know what that reaction might be. Don't know if destroying 3i Atlas would stop the mission or activate fail-safes that make the situation worse. It's a classic security dilemma. Action creates risk, inaction creates risk, and we don't have enough information to calculate which risk is greater, don't have frameworks for making these decisions, don't have precedent or doctrine or established protocols, so we watch and wait and argue and prepare for March 16th not knowing whether it will be the most important date in human history or just another day when a rock passed by a planet and nothing happened. The freight train is approaching the relay station. The cargo, whatever it is about to be uploaded, and humanity sits on the sidelines, unable to stop the process and uncertain whether we should even try. The whisper continues, low power, directional, possibly encrypted, possibly nothing at all, and we listen with instruments that might be adequate or might be completely inadequate, and we hope that if there's a signal, we'll recognize it, and we fear that if there is a signal and we miss it, we'll never know what was said. The destination changes everything, because 3i Atlas isn't just leaving our solar system, it's going somewhere, and when you trace the trajectory forward, when you calculate where the object will be in thousands or tens of thousands of years, you don't get a random point in the galaxy, you get a specific stellar system, Epsilon Tauri, a giant star in the Hyades cluster, 146 light-years away. That's not close. Light itself takes 146 years to make the journey. At 60 kilometers per second, 3i Atlas will take roughly 800,000 years to reach Epsilon Tauri, assuming the trajectory holds and nothing deflects it. That's an enormous timescale. longer than modern humans have existed, longer than most mammalian species persist in the fossil record, but in cosmic terms, in the lifespan of stars and galaxies, it's a blink. A single circuit in what might be a much longer journey. Epsilon Tauri is not a random target, it's a massive star, an orange giant that's exhausted the hydrogen in its core and expanded to many times its original size. It's old. The Hyades cluster, the stellar association that Epsilon Tauri belongs to, formed about 625 million years ago. That's young for a star cluster, but ancient by any measure of biological or technological timescales. Long enough for civilizations to rise, to peak, to decline, to migrate or transform or disappear entirely, and Epsilon Tauri has planets. We've confirmed at least one, a gas giant substantially larger than Jupiter, orbiting in the habitable zone where the star's heat is neither too intense nor too weak for liquid water, where if there are moons, those moons might have conditions suitable for life. The system is rich, complex, exactly the kind of place you'd expect to find either natural biological development or artificial settlement. If you were an advanced civilization and your home star was expanding into a giant phase, consuming the inner planets where you first evolved, what would you do? You'd leave. You'd build generation ships or upload yourselves into digital substrates or find some other way to preserve your existence beyond the death of your original world. And you'd look for new homes, new systems where you could re-establish, where you could continue whatever purpose or project defines your civilization, or you'd build a network, not just migrate once, but establish infrastructure that allows continuous exploration and communication across vast distances. You'd send probes to survey systems, you'd create relay stations for transmitting data, you'd use natural objects, asteroids and comets, as carriers, because building ships from scratch is expensive, and using what's already moving is efficient. And over millions of years, you'd create a web, a galactic transportation and communication system maintained not by continuous effort, but by the momentum already present in wandering objects. This is the network hypothesis. The idea that 3i Atlas isn't just going to Epsilon Tauri by chance, that it's part of a deliberate circuit, that it was launched from that system, or from a system connected to it, thousands or millions of years ago, that it's been visiting stellar systems across this region of the galaxy, gathering data, transmitting reports, possibly deploying sensors or seeds, and now it's returning home, completing the loop, bringing back everything it's learned to whatever awaits at Epsilon Tauri. Think of it as a bee returning to the hive. The bee leaves, searches for flowers, finds one, Earth in this analogy, and collects nectar, our data, our biology, our electromagnetic signatures, everything an observer could detect and record during a close flyby, and then it returns, performing the waggle dance that tells other bees where the food is, broadcasting the coordinates, describing what it found, enabling the next phase of whatever operation the hive is conducting. If that's what's happening, if 3i Atlas is reporting back to Epsilon Tauri, then the transmission at Jupiter becomes critical. Because you can't send data across 146 light-years using a 100-watt transmitter without amplification. The signal would fade to nothing long before it reached the target. But if you use Jupiter's magnetosphere as a relay, if you couple your transmission to the most powerful natural antenna in the solar system, suddenly interstellar communication becomes feasible. You broadcast at Jupiter, the planet boosts your signal, and the data propagates outward at light speed, taking 146 years to reach Epsilon Tauri, but arriving with enough strength to be detected and decoded. The lag is enormous but acceptable for a civilization operating on cosmic timescales. They launched the probe hundreds of thousands of years ago. They can wait 146 years for the data to arrive. And then what? What happens when the report reaches Epsilon Tauri? When whatever intelligence resides there, biological or artificial or something we don't have words for, receives information about a yellow dwarf star system with a life-bearing planet inhabited by technological primitives who've just barely figured out radio and haven't yet left their gravity well? This is where the speculation becomes darker. Because if you're mapping the galaxy, if you're cataloguing systems and resources and biology, then Earth is interesting, worth noting, worth flagging for future attention. But if you're harvesting, if you're extracting resources or collecting biological samples or eliminating potential competitors before they become threats, then Earth is a target. The panspermia angle suggested that 3i Atlas might be seeding life, distributing organic molecules across planetary systems to encourage biological development. That's a benign interpretation. a vision of elder civilizations nurturing the galaxy, spreading the conditions for life to emerge and evolve, and potentially develop intelligence. But there's an opposite interpretation. What if the organic molecules aren't seeds? What if they're bait? What if seeding planets with specific chemistry is the first stage of a much longer process that culminates in harvest? You distribute the precursors, you wait millions of years for biology to develop, you monitor from a distance, and when the biology reaches a useful stage, when it's created the compounds, or the diversity or the complexity you need, you return and collect. It's farming on a galactic scale, planting, waiting, harvesting, using timescales that make sense for immortal machines or uploaded consciousnesses, but that are incomprehensible to short-lived biological creatures like humans. If Earth has been seeded, if the organic chemistry that led to life here was delivered by ancient visitors, then we're not independent. We're not a random development. We're a crop, and 3i Atlas checking on our progress, measuring our development, reporting back to Epsilon Tauri, might be the scout determining whether we're ready for harvest. This sounds like paranoid science fiction, and maybe it is. Maybe the whole narrative is constructed from ambiguous data and pattern matching run amok. Maybe Epsilon Tauri is just the direction 3i Atlas happens to be heading, because that's where its trajectory points, and there's no intention or intelligence involved. Maybe the organic molecules in the coma are natural cometary chemistry, and the trajectory toward a specific star is coincidence, but the coincidences are stacking up. The trajectory precision, the structural integrity despite the size paradox, the low-power transmission limits suggesting stealth or directed beams, the fragment ejection at perihelion, the Jupiter encounter geometry, the destination at a system that's exactly the kind of place you'd expect to find advanced civilization, or at least its remnants. Each individual piece is explicable, but the pattern, the overall constellation of features, is harder to dismiss, and the stakes are high enough that dismissing it might be catastrophic. Because if the report reaches Epsilon Tauri, if the data about Earth gets transmitted, then in 146 years, whoever or whatever receives it will know we're here. We'll know our level of development. We'll know our atmospheric composition, our electromagnetic spectrum, our technological signatures. We'll have a complete profile of our civilization at this snapshot in time, and they might respond, might send a message back, might launch their own probes to gather more detailed information, might, if the harvest hypothesis is correct, dispatch collection ships to claim whatever resources they're interested in. The timeline is long. Even if they respond immediately, even if they launch something the moment they receive the data, it would take hundreds of thousands of years to reach us traveling at speeds comparable to 3i Atlas. We'd have time to develop defenses, time to become an interstellar civilization ourselves, time to reach a level of technology where we're not vulnerable to whatever they might send, unless they have faster-than-light capability, unless the 146-year light-speed lag for communication is bypassed by physics we don't understand, unless they can respond not in hundreds of thousands of years but in decades or even immediately. We don't know, can't know, don't have the data to assess probabilities, and that uncertainty is what makes the situation so paralyzing. Because if you act based on worst-case assumptions, if you treat Epsilon Tauri as hostile and 3i Atlas as a threat, you might be destroying something harmless and triggering hostility where none existed. But if you assume benign intent and you're wrong, you might be enabling an attack that you could have prevented. The transport hypothesis offers a middle ground, a way of thinking about 3i Atlas that's neither purely natural nor purely threatening. If it's infrastructure, if it's a resource available to any civilization that understands how to use it, then maybe we should be trying to exploit it ourselves rather than destroying it, or passively observing it. Avi Loeb's proposal to send human genetic material, to use the object as a carrier for our own data, is a response to this framing. If they're using the network, we should use it too. If they're sending messages, we should send messages back. If the galaxy is crisscrossed by these carriers, and we have the opportunity to add our payload, then not using that opportunity is strategic failure. The laser engraving idea is feasible. We have the technology to build megawatt-class laser arrays. Breakthrough Starshot is developing exactly this capability for a different purpose. If we repurpose those lasers, if we target 3i Atlas before it gets too far away, we could inscribe patterns on its surface, mathematical constants, representations of DNA, coordinates of Earth, whatever message we think might be decoded by intelligences examining the object in the future. The engraving would persist. would last millions of years, would travel with the object to Epsilon Tauri and beyond, would potentially be discovered by civilizations we'll never meet and that might exist long after humanity is extinct. It's a monument, a time capsule, a declaration that we existed and that we reached out. But it's also potentially dangerous, because a message can be interpreted as a threat, can reveal capabilities that we'd prefer to keep hidden, can mark us as worth paying attention to when anonymity might be safer. There's a concept in SETI called the dark forest hypothesis, the idea that the galaxy might be full of civilizations, but they're all hiding, all remaining silent, because broadcasting your presence attracts attention, and attention from unknown actors is dangerous. You don't know if the civilization that detects you is benign or predatory. Don't know if revealing yourself leads to contact and cooperation or to targeting and destruction. In a dark forest, survival depends on stealth. You listen but don't transmit. You observe but don't advertise. You develop technology quietly and hope that you become strong enough to defend yourself before anyone notices you're there. If the dark forest hypothesis is correct, then engraving messages on 3i Atlas is suicide, is announcing our location to predators who might otherwise pass us by, is ensuring that when the object reaches Epsilon Tauri and its surface is examined, whoever looks will know exactly where we are, and will have the information needed to target us. But if the galaxy is actually friendly, if advanced civilizations are cooperative rather than competitive, if the network is real and joining it requires demonstrating that you're capable of recognizing and using the infrastructure, then not sending a message is the failure. Is remaining isolated when connection is possible? We don't know which scenario is correct, don't have evidence favoring one interpretation over another, and the decision about whether to transmit, whether to engrave, whether to attempt physical payload, attachment, has to be made without that evidence, has to be based on philosophical assumptions about the nature of intelligence and civilization and galactic ecology. Different researchers have different assumptions. Loeb is optimistic, believes contact is more likely beneficial than harmful, believes that civilizations capable of interstellar travel have outgrown the territorial and resource-competitive behaviors that make humans dangerous to each other. Believes that the opportunity to communicate with potentially ancient intelligences is worth the risk of revealing ourselves. Others are pessimistic, believe that intelligence, regardless of substrate or origin, is fundamentally competitive, that resource scarcity drives behavior at every scale, that advanced civilizations might be even more dangerous than primitive ones because they have the capability to act on their competitive instincts across interstellar distances, that silence is survival and broadcasting is extinction. Most fall somewhere in between, uncertain, wanting to believe in friendly galaxies but aware of how often cooperation fails, even among human groups, hoping that we can reach out safely, but understanding that hope is not a strategy. And while the debate continues, while researchers argue about philosophy and risk assessment and message content, the object keeps moving. The distance from Earth increases, the window for laser engraving narrows. Soon it will be too far, too faint, too difficult to target with enough precision to create readable patterns. The opportunity is slipping away, and with it, potentially our only chance to participate in the network, to add our voice to whatever conversation is happening across the stellar neighborhood, to prove that we're capable of recognizing infrastructure and using it. Unless there's another way, unless the fragments provide an alternative. Because if 3i Atlas deployed objects in Earth orbit, if there are fragments sitting at Lagrange points, or in high orbits waiting to be discovered, then we don't need to catch the main carrier. We can study the fragments, learn from them, potentially reverse engineer whatever technology they represent. This is the retrieval mission scenario. Instead of trying to intercept 3i Atlas at its current distance and velocity, you focus on finding the fragments it left behind. You survey Earth's orbital space systematically. You identify objects that don't belong to known catalogues, and you send spacecraft to rendezvous with them and bring them back for analysis. It's technically much easier than intercepting the main object. The fragments, if they exist, are nearby, are moving at velocities we can match with current propulsion systems, are small enough to be captured and returned using existing spacecraft designs. We could launch a retrieval mission within months if we identified targets, could have fragments in laboratories within a year or two, and what we'd learn from studying them might be transformative. If they're technological, if they contain sensors or computers or propulsion systems, then we'd gain access to engineering principles we haven't discovered, might learn how to build better spacecraft, how to store energy more efficiently, how to process information using architectures we haven't conceived. It would be the greatest intelligence bonanza in human history, like Neolithic humans suddenly gaining access to modern electronics. The technological leap would be compressed from thousands of years of development into immediate acquisition through reverse engineering, but there's a risk, because if the fragments are designed to be recovered, if they're bait, then bringing them to Earth might be exactly what their creators intended. Might be importing threats directly into our biosphere or our infrastructure. Trojan horses, viral payloads, replicators that activate when certain conditions are met. We'd be studying them in laboratories with containment protocols designed for terrestrial pathogens and known physical threats. But if the fragments operate on principles we don't understand, if they exploit vulnerabilities we're not aware of, then our containment might be inadequate, might fail in ways we don't anticipate until it's too late. This is the dual-use dilemma. The fragments represent both enormous opportunity and enormous risk, and we can't fully assess which is greater without studying them. But studying them requires accepting some level of risk, requires bringing potentially dangerous objects into contact with Earth's environment. Different agencies are taking different approaches to this problem. Some advocate for remote study only, position spacecraft near the fragments, observe them in situ using instruments that don't require physical contact, gather data that might reveal function without the risk of contamination or infection. Others argue that remote observation is insufficient, that you can't reverse engineer complex technology from a distance, that if you want to understand how something works, you need to take it apart, need to examine components directly, need to run experiments that can only be done in controlled laboratory environments. The debate mirrors the older arguments about Mars sample return. Do you bring Martian material to Earth where you have full laboratory capability but risk biological contamination? Or do you study it in Mars orbit or on the Moon where contamination risk is minimized but analysis capability is limited? With the fragments, the stakes might be higher, because Martian biology, if it exists, is probably similar enough to Earth biology that we can contain it using established protocols. But alien technology might operate on principles that make containment meaningless, might be able to interface with systems remotely, might be designed specifically to resist the kind of isolation we'd attempt. So the question remains unresolved. Search for fragments but don't touch them. Search and retrieve but maintain extreme caution. Don't search at all and hope that if they exist they remain dormant. Each option has advocates, each has drawbacks, and the clock is still ticking toward March 16th, when the larger question of the Jupiter transmission will be partially answered regardless of what we decide about fragments. The meteor sightings continue, the orange fireballs, slow-moving, entering at shallow angles, could be fragments burning up in the atmosphere, could be natural meteors from sources we haven't identified, could be human imagination and confirmation bias creating patterns in random observations, but the satellite anomalies are harder to dismiss, the GPS disruptions, the unexpected drag, the signal degradation affecting multiple spacecraft across different orbits. These are quantitative, measurable, documented in engineering logs and operational reports. Something is creating drag in near-Earth space, something that wasn't there before December 19th or that wasn't producing these effects before then. Whether it's neutral particles from 3I Atlas's coma, somehow retained in Earth's vicinity despite solar wind, whether it's actual physical objects in orbit creating collisions and wake turbulence, whether it's electromagnetic interference from sources we haven't identified, we don't know, but the patterns are being studied, data is being collected and analysed, and if there are fragments, if physical objects were deployed, then the drag signatures and the orbital perturbations they create will eventually reveal their positions. Will allow us to target them for observation or retrieval. It's a waiting game. Collecting data, refining models, narrowing the search space, and hoping that whatever we find, if we find anything, provides answers rather than just generating more questions. Meanwhile, the main object continues toward Jupiter. The distance is now less than the Earth-Sun separation and decreasing daily. The approach trajectory is confirming predictions. March the 16th, 2026 remains the date when 3I Atlas will pass closest to the gas giant, and that's when we'll get answers, or at least different questions, because if Juno detects electromagnetic anomalies during the flyby, if there's evidence of artificial transmission using Jupiter's magnetosphere as an amplifier, then the artifact hypothesis becomes much harder to dismiss. Then we'll know with reasonable confidence that we're dealing with technology. And if we detect nothing, if the encounter passes without unusual signatures, then natural explanations become more credible. Then 3i Atlas returns to being probably just a weird comet, with unusual chemistry and trajectory but nothing that requires invoking intelligence. Either way, the object continues outward afterward, continues toward Epsilon Tauri on its 800,000-year journey, and we're left to process whatever we've learned and to make decisions about how to respond. Do we send messages to Epsilon Tauri ourselves? Use our own transmitters to broadcast information about humanity toward that star system? The signal would take 146 years to arrive, but it would get there eventually. Would potentially be received by whatever sent 3i Atlas, or by their descendants or successors. The METI debate, messaging to extraterrestrial intelligence, has been ongoing for decades. Some researchers believe we should actively transmit, should announce our presence and capabilities, should try to initiate conversation rather than just passively listening. Others believe any transmission is dangerous, that we should remain silent until we're much more advanced and can better assess the risks. If 3i Atlas is reporting to Epsilon Tauri, if that civilization already knows we're here, then the METI debate might be moot. The choice about whether to reveal ourselves has been made for us by the object's observations. Remaining silent becomes pointless if we're already in someone else's catalogue. But active transmission is different from passive observation. Broadcast shows capabilities, shows that we can generate coherent signals at interstellar distances, shows that we're not just primitive biology but technological civilization approaching the threshold of spacefaring capability. Does that make us more interesting? More valuable as potential partners or trading partners or sources of novelty and diversity? Or does it make us more threatening, more worth suppressing before we become competitors? The questions don't have answers, can't have answers without more data, without understanding who or what is at Epsilon Tauri and what their intentions might be, without frameworks for game-theoretic analysis of interstellar relations that we don't currently possess. So we default to caution, to waiting, to gathering more information before committing to irreversible actions. It's the conservative approach, the one that minimizes risk by minimizing action. But it also minimizes opportunity. Because while we're being cautious, while we're debating and studying and waiting for perfect information that will never come, the network continues operating. Other civilizations, if they exist, continue using the infrastructure, continue communicating and trading and coordinating across stellar distances using methods we're only beginning to suspect exist, and we remain outside, observers but not participants, aware of the traffic but unable or unwilling to join it, trapped by our own uncertainty and our fear of making mistakes. This is the cost of first contact when first contact is ambiguous, when it's not the landing on the White House lawn that science fiction prepared us for, when it's subtle and uncertain and open to multiple interpretations, when the evidence is strong enough to demand attention, but not strong enough to force consensus. We're left in limbo, unable to prove the object is artificial, but unable to prove it's natural, unable to dismiss the risks but unable to quantify them, unable to ignore the opportunities but unable to confidently seize them. And 3i Atlas continues its journey, indifferent to our confusion, following physics, executing whatever mission it might or might not have, approaching Jupiter on schedule, the transport hypothesis, the network theory, the harvest scenario, the panspermia angle. All of these are frameworks we've constructed to make sense of ambiguous observations. Stories we're telling ourselves because humans need narratives, need patterns, need meaning even when the data doesn't definitively support it. Maybe they're all wrong. Maybe 3i Atlas is just a rock, just a chunk of ice and stone that happened to form around another star, and that happened to pass through our solar system on a trajectory that looks designed but is actually random. Maybe we're seeing agency where none exists, projecting intention onto natural processes because we're wired to see minds even in mindless phenomena. Or maybe we're right. Maybe the object is exactly what the patterns suggest: technology, infrastructure, a participant in a galactic network that's been operating for millions of years, and maybe our recognition of it, our ability to detect and analyze and speculate about it, is the test, the threshold we need to cross to be invited into the larger conversation. We won't know until March 16th, until the data comes back from Jupiter. until we see whether transmission occurs or whether silence confirms that we've been chasing shadows. And even then, we might not know, might be left with uncertainty, with observations that support both interpretations, with results that don't cleanly favour either the natural or artificial hypothesis. But we'll be closer to answers, we'll have more data, we'll be able to refine our models and improve our predictions and prepare better for the next interstellar visitor, because there will be a next one, and a 10th and a 100th. The detections will continue, the population of known interstellar objects will grow. And with each new example, we'll build understanding of what's typical and what's genuinely anomalous. 3i Atlas is the third data point, unusual but not definitive, strange but not conclusive, important but not transformative by itself. The transformation comes from the accumulation, from the pattern that emerges when you have enough examples, from the statistical framework that lets you confidently distinguish between natural variation and intentional design. We're not there yet, won't be for years or decades, but we're building toward it. Each observation brings us closer, and in the meantime, the object speeds toward Epsilon Tauri, carrying its cargo of ice and rock and possibly data, travelling the ancient routes between stars, following trajectories determined by gravity and possibly by purpose. 800,000 years from now it will arrive. We'll enter that stellar system, we'll pass through whatever exists there and potentially interact with it. We'll complete its circuit and possibly begin another, and we'll be long gone. Humanity as it exists today will be extinct or transformed or scattered across the galaxy, or collapsed back to pre-technological states. Our civilization will be archaeology. Our debates about 3i Atlas will be historical curiosities if they're remembered at all. But the data will persist. The observations we're making now will be preserved in archives and databases, will be available to whoever comes after us, will contribute to understanding that accumulates across timescales longer than species survive. That's the real legacy of 3i Atlas, not whether it's natural or artificial, not whether we succeed in messaging it or retrieving its fragments or intercepting its transmission, but that we noticed it, that we studied it seriously, that we asked hard questions and developed frameworks for thinking about interstellar visitors that our descendants can build on. We're learning to live in a galaxy that's not empty, that's populated by travellers, whether those travellers are conscious or not, that's connected by networks of material and information and possibly intention. And we're taking our first uncertain steps toward participating in that larger system, toward becoming not just observers but actors, not just recipients of cosmic traffic but contributors to it. The journey is measured in centuries and millennia, in scales that make individual human lives irrelevant, except as small contributions to the larger arc of civilization. But the arc is real, the progress is happening, and objects like 3i Atlas, whatever they ultimately turn out to be, are the waypoints that mark our path from isolation toward connection. The transport is leaving, the relay is approaching, and we watch with instruments and minds barely adequate to the task, trying to understand what we're witnessing and what role we might play in whatever system we've stumbled into. The answer won't come on March 16th, won't come cleanly or completely, but it will come eventually, through patience and observation and careful analysis and the slow accumulation of evidence. That's how knowledge builds. 3i Atlas will fade from our instruments, will become memory and archived data, will join the catalogue of mysteries that future generations will have better tools to investigate. But the questions it raised will remain, will drive research and observation and policy for decades, will shape how we think about our place in the cosmos and how we prepare for the next encounter. Because the next encounter is coming, the freight trains keep running, and eventually we'll figure out how to catch one, or one will catch us. Either way, the age of isolation is ending, the age of interstellar awareness has begun, and 3i Atlas, whatever it is, wherever it's going, whoever might be waiting at Epsilon Tauri, has shown us that we're not alone in the dark, that the galaxy is active, that the distances between stars don't prevent connection, they just make it slow and patient and strange. Keep watching, keep listening, keep looking for the patterns that reveal what's real beneath the noise, because the signal is there, faint, encrypted, possibly not meant for us, but there, waiting to be decoded by minds ready to understand it. The transmission continues, the network operates, and humanity, Uncertain and divided and barely beginning to comprehend what it's witnessing, stands at the threshold of joining something vastly larger than itself, or remaining outside, safe in isolation, protected by ignorance. The choice, to the extent we have a choice, is being made right now, in the debates and decisions and actions we take in response to this visitor and the next. Choose wisely, watch carefully, and never assume that silence means we're alone. Sometimes silence just means we don't yet understand the language.